What we have in front of us is a periodic table of elements, except it's kind of special. It's not like the other one that we have been using, or it's not like one that you normally see. This one is special in the sense that it tells you what are called electronegativity values for most of the elements on the periodic table. For some of them, we actually can't know the electronegativities because some of them exist so transiently, they just kind of like disappear before we even have a chance to figure it out. For the rest of them, however, for most of them that we're going to be using, we actually do know that. Now, here's the thing. I'm talking about electronegativity, but really you might be having the question, well, what is electronegativity? Well, electronegativity is actually pretty straightforward. When you think about an atom, you realize that it has a positively charged nucleus. And then the other thing to consider is that if you have an electron kind of just chilling on the outside of that atom, that has a negative charge. You have a nucleus that has a positive charge. Whenever you have opposite charges, they have a tendency to attract. And so when you have that there, that nucleus is going to be giving some attractive force where it's going to try to pull in that electron. And the stronger that tendency to want to attract that electron in, the more electronegative that atom is. So electronegativity is just that. It's the tendency for an atom to want to attract electrons towards itself. The more electronegative, so if we're thinking about someone like fluorine, right? So on that corner on the periodic table, fluorine is the most electronegative element on the periodic table. It really, really wants to put electrons towards itself. By contrast, if you look all the way to the other side of the table, you go to the opposite corner. If you go over here to francium, and I'll circle him too. So if you're talking about francium, that's like the complete opposite. That dude doesn't really even care about his electrons. He's just kind of like whatever. Okay, so we have those kind of two extremes. Now, the title of this video is not electronegativity. The title of this video is, what is bonding character? Okay, well, first of all, what is a bond? If you don't know what a bond is, you can keep it very, very simple. You have element A, you have element B, and the thing that you need to ask yourself is, well, a bond is pretty much how do A and B come together? In what way? And that's what we're going to be kind of talking about right now. This might be a review. This could be something of a new topic. I'll approach it like it's relatively new just to go over the basics, and then we'll take it from there. Now, here's what you need to consider. You have elements, different elements, two of them. You have A and B in this case. Doesn't matter which elements they are because the fundamental principle is still the same. If there are electrons in between them, A is going to pull that electron towards itself, and then B is also going to want to kind of pull that electron towards itself. And maybe there's going to be, a difference in how they pull it. But essentially what we have here is the makings of an electronic tug-of-war, where they're fighting over this electron and they're going to see who's going to take it. Now, this is important because if you've gone over the other videos, you know that valence electrons are a thing, and valence electrons, again, are the electrons in the outermost shell. However, valence electrons are also called bonding electrons because they are the ones that actually pretty much govern how bonding between elements works. And so what that means then is that we have to really think about what's going on here so that we can start to begin to understand how this bonding is going to work. And so I'm actually going to operate off of the first example, which is to take the extremes and then see what's going to go on here. So to kind of draw this out, we're talking about francium and we're talking about fluorine. So we're talking about francium. Now francium again is a guy, and he's gonna be pulling on that rope, whatever it is, with a certain level of tug. And then you have fluorine essentially on the other side, who's also going to be pulling, trying to really get those electrons for itself with his own level of tug also as well. And so what are they fighting for? Well, again, electronegativity is a tendency to bring in electrons. So they're really fighting for an electron. But then you need to start thinking, okay, well, who's going to win? Right? You need to start asking, okay, well, who's the stronger one? Who's going to be having the bigger pull? Well, that's why we have the electronegativity table. When you look up at the electronegativity table, if you look at fluorine has essentially an electronegativity value of around 4. So if we're thinking about what fluorine is going to do when it pulls towards itself, fluorine is going to pull towards itself with about 4.0. I'm just rounding. But then if we look at francium's over here on the left side, right? Just to remind you, francium's over here. You have an electronegativity value of 0.7, and so that means then that if you're talking about francium's going to pull towards itself with 0.7. It should be plainly obvious who's going to win this tug of war. And in fact, it's going to be a huge difference, because when you actually do check the difference, and again, this is actually how you check to see what bond character is like. You look at the electronegativities for each element, and then you check for the difference. You look for the net. It's going to be 4.0 minus 0.7, and then that tells you that there's going to be a difference of 3.3. And it's very obvious that since we know fluorine is going to win, the fluorine is going to win with about a 3.3 magnitude over the francium. That's a pretty big difference. The way you want to analogize is that it's pretty much like a 310-pound lineman going up against maybe like a 7 or 10-year-old or whoever, just a little kid. And you can kind of imagine that in your head right off the bat, that fluorine is probably going to win. And in fact, it's going to win to such an extent that if you think about what's going to happen here, that electron is probably going to get straight up pulled all the way pretty much towards the fluorine, because the fluorine wins the tug of war to that extent. Now, what does that mean, though? Because we still need to contextualize that within the chemistry. What does that look like? Why does that bring up bonds? Well, we were talking about Lewis dots, and so we need to come back to that. So if you think about francium, look, francium is in group 1, and you can see it there. Francium is in group 1, and so that means it's going to have one valence electron. Fluorine, again, is in group 7a, and so that means it's going to have 7 valence electrons. Now, fluorine pulls with such a force on its electronegativity, and that difference is so huge, and that difference is the most important part, that fluorine can actually take the electron away from francium, because francium isn't really that likely to keep it. And so what that means then is that when fluorine picks up that electron, fluorine has its octet. When francium loses its valence electron, it goes down to the lower shell and it has its octet. Everyone has their octet. Everyone is happy. And so that means then that when this happens, fluorine has a positive charge because it lost an electron. It becomes a francium. Francium loses its electron. It becomes a positive charge. It becomes a cation. Meanwhile, on the other side, fluorine gains a negative charge. It becomes an anion. We've made ions. And in fact, we made a positive and we made a negative charge. And so if you take that to its logical conclusion, what that means then is that the francium now has a positive charge, and it's going to come together with the fluorine that has a negative charge. And just like that, the atoms have come together and they've bonded. Now, because we made ions, again, right, cation, anion, because we made ions, we call this an ionic bond. And so really the key takeaway is pretty much this. Because the difference in electronegativity is very large, so because this is a very large difference, in those cases you can actually transfer electrons. And when you transfer electrons, you make ions. And if you make ions, they can attract to each other and you can make an ionic bond. Okay, so that's if we have very large differences. All right, cool. Well, that means that we need to consider then, well, what happens if we actually have, let's go to the other side of the spectrum. What happens if we actually have a very, very small difference? What happens then? Well, when you have a very small difference, the behavior is going to change. And in fact, it's going to change entirely because it changes the entire dynamics of the tug of war. And so the easiest way to do this is that we can kind of keep working with fluorine, although it doesn't necessarily matter, but we might as well go all the way to the opposite extent. So if we're working with fluorine and we're thinking about fluorine with fluorine, we might draw that again. You now have fluorine, and again, this guy's going to be pulling on that rope with its own strength. And then on the other side, again, you also have another fluorine. Let me actually draw that a little bit better. Now we can actually show it. Not that I should really care too much about stick figures, but it doesn't really matter. On the other side, we have this fluorine as well. And that guy is also going to be pulling on the tug of war. And then we need to start thinking, all right, well, what's going to happen to this electron? Well, now we've gone all the way to the opposite extreme. This fluorine is going to be pulling to itself with 4.0 because, again, we know the electronegativity of fluorine. We used it for the last example. However, if we're going to be bonding it with fluorine, that other guy is also going to be pulling with 4.0. So in this case, instead of it being like a huge difference where we have essentially like what's the equivalent of a 300-pound lineman trying to fight a 7-year-old over, I don't know, like a toy or something, or just having their tug of war, we now have pretty much the equivalent of a 310-pound lineman trying to fight a 310-pound lineman. There really isn't going to be a winner here. That electron really isn't necessarily going to be going anywhere. And so what that means then is that even if you look at the net and you check the difference, well, the difference is 4.0 minus 4.0, that's just going to be 0. That electron isn't going anywhere. So whereas before, when you had a very large difference of electronegativity, you could actually rip the electron away and transfer it, things are a little bit different here. Because no one is really going to be winning out, the only option that they have then, if they both want to complete their octets, is to share. And so, well, what does that look like? Well, if you look at fluorine, and again, fluorine is in group 7, so it has those 7 valence electrons. Fluorine has those 7 valence electrons. The other fluorine has also its 7 valence electrons. They're going to need to want to complete their octet. No one is going to be able to transfer an electron over and so on and so forth. That's not really going to happen. They want their electrons too badly. It's just not possible. So the compromise has to happen. Now, the easiest way to think about a compromise is essentially to just think, okay, well, if they each need to complete their octet, there's something very kind of crucial going on here. We know that electrons like to have pairs, and look at that. We have missing spots on each one. So what's the easy solution? Well, hey, you have a free electron, I have a free electron. We need to make a pair. Let's make a handshake. Let's just kind of cooperate. And so when that happens then, when you actually do the bonding, it might look a little like this, where you still have those 7 valence electrons on one fluorine. But then if you kind of consider the other fluorine, it might look a little something like this. And then this is very important because then if you consider what's going on, well, this fluorine has its octet right there. You can see those 8 electrons around it. And the other fluorine also completed its octet. And so what happened here was that they pretty much shared those 2 electrons in the middle. And so in a certain way, we can actually rewrite this to show that by using a line. That line represents a pair of electrons that are being shared in between the two, the two atoms. And so there's a bond. We have a new type of bond. And so what happens then here is that when you consider this, you now need to kind of think of another word. And so what the word that we came up with was pretty much that when you have these valence electrons, and again, the Lewis dots do tell you what the valence electrons are, we now know that those electrons are being shared in this bond. So this type of bonding is different from an ionic bond because in this case, what's going to happen is that you're going to have something called a covalent bond. And the reason, again, why it's called covalent is because if you pay very close attention to the word, you see co, and then you see valent, which valent refers to the valence electrons. Co, you can think about it as it meaning combine or cooperate or whatever, just a word that means together. And so you have your covalent bond. And so the nature of this, again, really is that you need to think about the electronegativity difference. And in this case, the electronegativity difference was really small. It's 0. So when you have an electronegativity difference, so a difference in electronegativity that is very small or lower than a certain threshold, you actually end up having something called a covalent bond. Because in this case, instead of transferring, you're forced to share electrons. And anytime you share electrons, you're going to have a covalent bond. Why? Well, because, they have, essentially both have a very strong pull on those electrons. And so neither one of them are really going to want to give them up, like in the other case for ionic. You're not making ions. They're just kind of sharing electrons. That's it. And we have no real charges. Okay, well then what's the cutoff? At what point do you have a difference? Well, this is giving us the beginnings of what you might consider to be a spectrum that you can work with. And that spectrum is going to have certain areas where things might bend the rules a little bit. And then you also need to kind of consider, certain scenarios that are going to be somewhere in between. Because if you think about it and you keep it very simple, you can begin to actually write the beginnings of a spectrum where you have a line, and it goes this way where it's increasing and then it goes this way where it's decreasing. And if you're thinking again about differences in electronegativity, so if we're talking about differences in electronegativity, when you have very large differences, you're more ionic. And when you have very, very small differences, almost even non-existent, you become more covalent. However, now that you have the beginnings of the spectrum, you're starting to think, okay, well, where's the cutoff? Right? Like, where do we ultimately decide that there's enough of a difference in the tug of war that we can actually strip electrons or transfer them? Where is that line? How can we decide that? Well, it just so happens that the line happens to be around 1.7 or 1.8, one of the two, around there, and that's the general vicinity. Once you pass that threshold, you actually have enough of a difference that you can begin to transfer electrons in this area. You can transfer electrons so long as you're in this general vicinity, that kind of idea. However, just because you're sharing electrons on the other side does not necessarily mean that you're going to share them evenly. Because when you start talking about the other end of the spectrum, where essentially you're talking about zero difference over here, well, you need to start thinking, all right, well, what happens somewhere here? Because they're not necessarily going to share equally. Well, the cutoff in this case, and again, we can kind of go through this, but it really just has to do where you think about it. Pretty much, the more you go to the right, the more ionic you become, which means that the more you go to the right, the more you get closer and closer to actually separating electrons and then creating complete charges. There's a secondary cutoff in the covalent area where at around what's essentially a difference of around 0.4, you actually share electrons evenly. And so that in itself is actually something called a non-polar covalent bond. However, in this area right here, that is actually where you start to have the situation where you do not share electrons evenly. You actually share electrons unevenly. You're still sharing, so you're still covalent, but you're sharing them unevenly. And in this case, this is called a polar covalent bond. And so this is essentially kind of the basics of bond character. You have a very simple set, which is when you look at this and you need to think of kind of like an overhead difference, you have covalent versus ionic, and that's kind of divided up by that section point right there at around 1.8. But then even within covalent, because you still need to think about how the electrons are shared, you also have something else that you need to consider, which is, what is polar, what is nonpolar. But essentially, these are the basics of, bond character. I'm going to go more in depth into the individual types of bondings in separate videos, but this is kind of like the introductory launching point to really begin to understand the rest of them. And to be honest, it serves as a good review point as well.